Now we're going to finish up the different types of transformations, and we're going to talk about stretching, shrinking, and reflecting graphs. So first we're going to talk about stretching and shrinking. And honestly, there's not too much of a difference between these because you're going to notice one will translate to another. And all this does is it really makes the graph either wider or thinner. So just depends in which direction you're applying like a weight to, basically. So you're going to start with a graph of f of x again. And a stretch or shrink is just going to be multiplying by c in a specific spot. So if we put the c outside, again, it's not directly attached to x, this is going to be a vertical stretch or shrink. If it is attached to x, it means we're going to affect it in the x direction. So it's a horizontal stretch or shrink. For vertical, it does exactly what you would expect. So the difference between these two is purely based on the specific value. So if the value you multiply by out front is bigger than 1, so think of this as 5 times x squared, it's going to make all those y values much larger, and this is going to mean we're going to stretch the graph of the original function in that y direction by a factor of c. If instead you multiply by a fraction between 0 and 1, so this means I take 1/2 of my previous values before, this is going to indicate we're going to shrink that graph vertically by a factor of c. When it's on the inside again, it's going to have the opposite meaning. So you would think if I had 3x inside of my graph, that would stretch it in the x direction, but it does the exact opposite. This is actually going to shrink it vertically. And then if I have a fraction on the inside between 0 and 1, instead of shrinking my graph horizontally, it's going to stretch it. So it does the exact opposite. So you don't have to make a serious mental note as to what the names of everything are. It does not move any points, or it doesn't move like the graph around per se. It just is going to make it thinner or wider. So what I want to do is I want to just compare with two different examples based on where we put that value. So for these ones, we're going to start with our absolute value function, and we're going to graph y equals the absolute value of x, y equals 1/2 the absolute value, and y equals 2 absolute value on the same function, or on the same plot. So we're going to draw this nice and big, okay, because our absolute value function doesn't have negative numbers. So I'm going to go ahead and I'm going to go out 5 in each direction. Yeah, need a little more up here, so 6 is fine. 1, 2, 3, 4, 5. Okay. And I'm going to start by graphing our absolute value function. You plug in 0, it goes through 0. You plug in 1, it goes through 1. And I'm going to keep track of this point here. When I plug in x is 2, my y value is 2. And then you get the graph going in this direction. When you plug -1 in, you still get +1. When you plug -2 in, the absolute value of -2 is 2. So this would be our graph of the absolute value function. Now what happens is when I go ahead and apply this 1/2 and this 2 out front, again, it's not attached to x, so it's impacting my y values. So when I start with this graph, if I plug 0 into it, it still is going to go through 0, 0. But now think, if I plug 2 into here, this would be 1/2 times the absolute value of 2, which is 1/2 times 2, which means my new y value corresponding to x equals 2 is 1. So my point gets cut in half. Okay. And then the same thing, if I plugged in -2, it really makes no difference because the absolute value of -2 is still +2. my y value is 1. So this is our graph of 1/2 absolute value of x. So you can see we've taken that graph and it's basically like we've applied a weight sitting on top of it to shrink it down to here. So it's compressed that graph quite a bit. Or you can think of if you hold the very ends of this absolute value function, you shrunk it by moving it down in the y direction. For this function, it's going to have the exact opposite effect. It's like I'm taking the ends and I'm picking them up and stretching this guy out. So if I plug in 0, you're still going to go to 0. But now if I plug in x equals 2, this will give us 2 times 2. My y value corresponding to 2 has now doubled up to 4. Okay. So I've taken this graph and I've moved the ends up to get my new one, and I've made a thinner graph in return. And then the same thing, if I plug -2 in, you're still going to get +4. Okay. So again, it doesn't impact a ton, it just impacts how thick or thin this thing is. So let's try now instead putting that 1/2 on the inside, directly attaching it to the x value. In this case, what I want to actually do is not quite the same as the last one. So just to go back for a second, here I kept the x value the same and I saw what happened to y. Now for this, I want to do the opposite because the number is attached to x. So I want to basically see what x do I need to plug in to keep my y value the same. And so I'm going to go out again as much as I need to, but it looks like about 5 will be sufficient. And we'll start by graphing our normal absolute value function, which goes through 0, 0. And again, I'm going to keep track of this point at 2, 2 for all of them. And then it goes through -2, +2 as well. Okay. And so for this first function, when I have 1/2 x on the inside, again, I want to see what x do I need to plug in to give me a y value of 2. Right? So if I think about this, what we would have to do is if I plug in 4, this would be 1/2 times 4, which gives us the absolute value of 2, which is 2. So now instead of plugging in x equals 2, I need to plug in x equals 4 to get the same y value of 2. Okay. So you can see, you would think that 1/2 would shrink it, but it's actually taken the x and it's stretched it out to here. And then same thing, if you plug in -4, you would see the y value is +2. So it has the exact opposite effect when it's attached to x. For y equals 2x, if I plug 1 into this expression, I still get the absolute value of 2, which is 2. So I actually now go through the point 1, 2. So I've taken this point and I've shrunk it inwards to get the other shape of our graph. Okay. So larger values attached to x shrink the x. And then you would see if you plug in -1, it would still go through +2 as well. Right? So exact opposite meaning for these two. Right? doesn't impact the overall moving this around in any way. It doesn't change like your main starting point. Instead, it just changes how wide or thin. But if you really notice from these last two, they're honestly exactly the same picture. So in this case, because it's the absolute value function, these numbers can pop outside. They don't have an impact at all inside the absolute value. So one will always correspond to another. All right, so what we want to do to actually lead into reflections is I want to start by comparing what two graphs look like. And so a reflection is always going to be indicated by putting a minus sign somewhere where it wasn't originally there. So we're going to start by comparing the graphs of y equals x squared and y equals negative x squared. And what I'm going to do, I'm going to do a little more detail with this. I'm going to pick some x values, and then I'm going to go ahead and plot what x squared is. And then I'm going to pick those same values, and I'm going to see what the y values are for this other graph. Okay. And then we'll go ahead and we'll plot both of these on the same picture. So for both of them, I'm going to pick -2, -1, 0, 1, and 2. And same exact x values over here. Okay. I'm actually going to move this right down here. So if we plug these values in, for the first one, this would be -2 squared. So the y value would be +4. This is -1 squared, which is +1. 0 squared is 0. 1 squared is 1. And 2 squared is 4. For this other graph, this minus, remember, is on the outside. So I've got to replace x. It's x that's being squared. So this is really -2 squared. So when I take -2 and square it, it's +4. This minus sign happens afterwards because you always handle the exponents first. So the y value is -4. When you plug -1 in, same thing. So this would be -1. If you plug in 0, well, it's still 0. And if I plug in 1, this will still be -1. And when I plug 2 in, you get -4. So if I go ahead and graph these, I need to go out 4 in the y direction. 1, 2, 3, 4. 1, 2, 3, 4. And then 1, 2, 3 is enough because I only went out to 2 and -2. So we'll start with graphing y equals x squared. Goes through 0, 0, then 1, 1, and 2, 4, -1, 1, and -2, 4. So this is our graph of y equals x squared. Now when I graph negative x squared, it also goes through 0, 0. But when we plug in +1, it's -1. +2 gives us -2. And then the same thing down here. So my graph actually goes downwards now. Okay. So the only difference between these two graphs are the minus sign here. And it's not attached to the x. I know it kind of looks like it is, but really think of this as -x squared. So it's not inside, it's on the outside. So because it's not attached to x, what actually happens is we've taken this graph and we flipped it over the x-axis. So this actually corresponds to an x-axis reflection. For this one, now let's see what happens if I do put the minus sign directly on the x value. All right, so it is impacting my x values. So again, I'm going to make two charts. I'm going to graph y equals the square root of x, and then we're going to graph the square root of -x. So remember, we had to be careful with our square root function. We don't want to take the square root of a negative number. So for this first one, I can plug in 0. This would be the square root of 0, which is 0. I can plug in positive 1. That gives us the square root of 1, which is 1. And I'm going to pick another nice number. If I plug in 4, this gives us the square root of 4, which is 2. Okay. When I go to this next one, I can't pick a lot of these same x values. You can plug in 0, because that would be the square root of negative 0, or just square root of 0. But if I try to plug in positive 1, you run into a bit of an issue. You'd end up with the square root of negative 1. So I actually can't do that x value. Instead, let's try plugging in negative 1. This would be the square root of negative 1, which gives us positive 1 underneath that radical. So we end up with positive 1 as the output. So really the only kind of numbers I can plug into this expression are negative ones. So this would be the square root of negative 4, which is the square root of positive 4, which gives us 2. So this has impacted the x values that we can use. So if we go ahead and graph this one now, again, we're going to graph it super precise just for this example. Okay. So we'll start with the square root of x. It goes through 0, 0, 1, 1, and 4, 2. And it has the kind of square shape. That's the square root of x. And now I've got to plug in negative 1 to get positive 1, negative 4 to get positive 2. So my graph is actually flipped across the y-axis. So this minus sign being directly attached to x actually tells us to take the original shape and flip it over the y. So this is exactly what our reflections mean. I'm going to start with that function y equals f of x. If I attach a minus sign directly to x, it means flip the graph of the original function across the y-axis. If I put the minus sign on the outside, so it's not attached to x, meaning it's impacting y, this tells us we're going to flip it across the x-axis. Okay? So with all of these new transformations, the order now really does make a difference. If you don't stick to this order, you can't use this method that I'm about to show you. So you want to think of your order of operations. These minus signs can be attached in a couple of different spots. So I'm working with a very specific example. But the very first thing you always have to do with your order of operations, think of your PEMDAS. So let me write that out. For transformations, exponents don't mean anything because we don't have a rule corresponding to adding an exponent in anywhere. So the first thing we need to do is we need to work inside parentheses. So just based on this example alone, I'm going to go inside my parentheses and I'm going to go ahead and I'm dealing with that plus 4. So the very first thing I need to do is that vertical or horizontal shift because it's attached to x. So you always want to start with your horizontal shifts. Okay. Then after I've gone inside those parentheses, I can go ahead and deal with multiplication and division, which is like timesing it by a half. So moving out front, this minus 2 is really two different transformations. The 2 is a stretch and compression, and then that minus sign is a reflection. This one, the order doesn't matter because multiplication is interchangeable. What I would tell you to do is move to stretches and shrinks next. And then the third thing you want to do are your reflections. Okay. And so that takes care of multiplication and division. So that moves on to addition and subtraction, which is this last lonely thing out on its own, which is our vertical shifts. Okay. So again, as long as you start with horizontal end with vertical. The stuff in the middle doesn't really matter, but you do have to always do horizontal shifts first. If you don't do this, you're going to get the wrong graph. So let's try an example. So I'm just going to do one example in this video, but I will post a supplemental one that I've just found on YouTube that's really good for you to go through. We're going to sketch the graph of this function, which has a ton of transformations applied to it. So what I do want to do is I want to rewrite this just a little bit. Let's write this as negative x plus 3, just because we're used to the squared x and then adding or subtracting something from there. So we've got 3 transformations here. We've got a minus sign attached to the x. We have a plus 3 also attached to the x. And then we have a minus 2 on the outside. So thinking about what each of these does, the plus 3 is a horizontal shift. The minus 2 is a vertical. And then this minus sign indicates some kind of reflection. Okay. So what we're going to do is we still start with our normal graph, and in this case we're dealing with a square root function. First thing we have to do is that horizontal shift. And so when I have a plus 3, this indicates we shift left 3. Okay. Now we move on to our reflection. I have a minus sign attached to x, so that means we're going to flip or reflect across the y. Okay, so this is our second step, and this is our first. And then our third step is we have that minus 2, so we shift it down 2. Okay. So I've got 3 transformations. That means I'm going to go ahead and draw 3 graphs. So I'm going to move this up in the corner just to make things easy. And let's go ahead and draw 3 graphs. So here's x, here's y, and I'm going to go out 4 in every direction. Transformations, 3 graphs. Let's see if I drew it so they all fit. Okay. Let's do that one down and then move this one like up here. There we go. Now I can make them a little bit smaller. Oh, missed a piece. Oh. All right, let's just do this then. Get rid of this one, and then we'll copy and paste the shrunken version. There we go. Now we can fit everything. Okay, so we got to start with our square root function, and again I'm going to keep track of this point at 0, 0, and the square root function just goes sideways like this. So this is our graph of the square root of x. First thing I do is move it left 3. So this point is at negative 3, 0. And then it has the same shape. And if I want the equation, it would just be that single transformation of plus 3 on the inside. Now, this was our left 3. Now we're going to go ahead and we're going to reflect it across the y-axis. So I'm going to go sketch in this graph again at negative 3, 0. And it looks like this. To reflect it across the y-axis, this point at negative 3, 0 would get moved to positive 3, 0. and then our graph would go in the opposite direction. So again, if you were to kind of cut this right down the middle, you would see folded up, you have the same picture. So that's its reflection. So this right here would be the graph of just negative x plus 3 inside the square root. Right? And now I'm going to take that picture and let me go ahead and write my point here at 3, 0. And I want to go ahead and move that down too. So our starting point gets moved to 3, negative 2, and then has that same overall shape. And this is the graph of all of these transformations now applied. Okay. And again, I can double check myself with at least this one to make sure that I'm picking the right x values. Our domain is negative infinity up to positive 3. So if I try to plug 4 into this expression, that would be the square root of 3 minus 4 minus 2, which gives us the square root of negative 1 minus 2, and that makes no sense, okay? So you can see these ones take quite a bit longer just to apply everything together. So I will post, again, a supplemental video with just more examples if you do need that. Your homework should also have some videos within there, or you can click through the Help Me Solve This to see what's going on. Instead, I want to do one last type of example where, given a function, I want to go ahead and apply transformations to that graph. So it's not one of those basic shapes we've had before. And so this way we can go through those stretches and shrinks as well here. So we're given this graph of f of x, which has kind of this line shape. So it's two different lines put together. And the first thing I want to do is I want to sketch 2 times this function. So again, that 2 being multiplied means it's a stretch or shrink. And because it's not attached to x, it's impacting those y values. So what that 2 times does is it takes all those y values that you had before and it's going to double them instead. So what I kind of want to show you is just through walking through point by point. We have all of these labeled out. So when you plug negative 2 into this function, the output is negative 1. When I plug negative 1 into the function, the output is positive 2. And when we plug 3 into the function, the output is positive 1. So what I can do is I can now plug those same x values into this expression to see what y corresponds to it. So in the case when we plug negative 2 in, this would be 2 times f of negative 2. Well, f of negative 2 is negative 1. So this function goes through the point negative 2, negative 2. So this y value gets doubled. All right. When I plug negative 1 in, that'd be 2 times f of negative 1. F of negative 1 is 2. So my new y value corresponding to negative 1 is positive 4. So this y value got doubled. When we plug 3 in, it'd be 2 times f of 3, which is 2 times 1, or 2. So my new y value is 2. So again, this y value got doubled. Okay. So if we go to graph this, my y values are going to be a lot bigger. So let's go up 1, 2, 3, 4. So our original point went through negative 1. Now, for that same x value, it goes through negative 2. This point originally went through -1, 2. That y value got doubled, and it goes through -1, 4. And then same thing here. It went through 3, 1. It now goes through 3, 2. So those y values got doubled. But then it still keeps that same straight line shape. Okay. So that 2 on the outside only impacted the y's. If instead I change this problem up slightly and we were to graph f of 2 times x, instead of multiplying x by 2, it's going to do the opposite effect, and it's going to cut the x values in half. So always the opposite with x. So let's just do one more example, and we're going to do 1/2 times f of x minus 2. So we have two transformations really. The first one is just dealing with the -2 on the inside, and then applying that 1/2 on the outside. Or we can even make this a little bit harder. Let's change the problem up so you can see what I mean. Let's put a 1/2 on the inside. Right, so I'm going to change this so we can see that x value. Right. So the very first thing, this -2 tells us we're going to move it to the right 2. So I want to take this graph that I had, and I'm going to even cheat a little bit again. And I need to move everything to the right 2. So I actually have to go out further here to 5. So this point gets moved to the right 2. This point gets moved to the right 2. So it'd be -1 or +1, 2. And then this point gets moved to the right 2. It goes through 0, -1. So this would be our graph moved to the right 2. Okay. Now, when I put that 1/2 attached to the x, it's impacting x values. So I gotta move all this stuff around just to make some room to get this done. Okay. And I forgot to change that to 5. It didn't look like a 5. So what I need to do now is, you would think that 1/2 would cut the x values in half, but it's going to do the opposite. It's going to double them. So I really need to go out super far in this direction. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And then we'll go up still 3 and down 3. Okay. So I'm using this graph from above, and what I want to do is I want to see, okay, because I'm attaching this 1/2 to the x, what x do I need to plug in so that I get this same output here of -1? Okay. Thankfully, it's not going to do anything for the first piece, because if I cut 0, if I multiply that by 2, it does nothing. So it's still going to go through 0, -1. Okay. But now this point, I'm not affecting the y at all, because again, the 1/2 is attached to the x. And the 1/2 tells me I'm actually going to stretch it by a factor of 2. So this point is actually going to go through 2, 2. It's going to double, right? Same thing here. I'm attaching the 1/2 to x. It does the opposite of what I want. So instead of it cutting the 5 in half, it's going to double it, and it's going to go to 10. So it goes through the point 10, 1. Okay. So remember, the 1/2 is a horizontal stretch, so it makes our graph wider. So always when you're going through these problems, x does the opposite of what you would think.